Hi, so let's start. Welcome to today's tutorial. I will pass on the signature list again. So maybe a short organizational introduction to next Monday, because there we're gonna have two tutorial sessions, one in the morning, the other one in the afternoon. Maybe there was some kind of confusion, but the spot in the afternoon is gonna be just a normal tutorial session. All right. So let's start with a short recap again, what we have done yesterday. So we repeated some memory types, which are namely SRAM, DRAM, and ROM. So SRAM are two cross-coupled inverters. So they have a static load, consists of typically 6 transistors, and for the readout, they usually also need some sense amplifiers. So SRAM usually is very small and can be on chip, which makes them very fast to access. So for example, they are used in caches, which brings us to DRAM, which is dynamic random access memory that has a lot denser structure than SRAM has, and consists only of 1 transistor and 1 capacitor. You also need additional sense amplifiers for accessing the memory cells of a DRAM, and they are organized in large arrays of memory cells and usually are off-chip, so it's a separate DRAM chip and connected over a bus interface to the actual working chip, and this makes DRAM much slower than SRAM. And the other thing that is important about DRAM, as the name suggests, it's dynamic, so non-static, and requires refreshing after a certain time. Then the third memory type is ROM, so read-only memory. It is one-time programmable, and on an FPGA, it's just RAM, so SRAM. And once it has been initialized, you only read it. So that's how it works on an FPGA. Afterwards, we talked about, okay, what other types of memory or storing element could be used. So we talked about NOR-based latches, how they work, how they store values, how we set a value, how we reset a value, and also forbidden states. So if you reset and set at the same time, so what would you expect? So both of the outputs, Q and Q naught, are gonna be 0. This is something you should not do, and is also not really true. And what happens if you, after a forbidden state, switch to the set state again? The NOR latch or all latches begin to oscillate. How can we overcome those problems? So instead of latches, we use flip-flops. There, for example, we could use a poor JK flip-flop or a master-slave JK flip-flop, which both don't have forbidden states. Then there's also another possibility to build a latch, not only on NOR gates, but also using NAND gates, which makes one big difference, which is the sensitivity. Instead of set and reset being sensitive to 1, set and reset are sensitive to logic level 0. So what is the difference now between a latch and a flip-flop? So latches are level triggered, flip-flops are edge triggered. Latches do have forbidden states, which flip-flops don't. And latches can oscillate, and flip-flops do have meter stability. Then we already started with the topic we will focus today mostly on, which is the timing of digital circuits. We had a first glimpse at this register stage. So we have 2 registers, some combinatorial logic in between, And we already retrieved some logic functions for G, H, and I, and started to calculate the propagation delay for each of those paths. So for G, H, and I, it led us to those three results. So what you can see here is one of those has the longest delay, which in this case is TH. So this means that the critical path of those three is TH. And why is it called critical? Because this is like the longest path, and we will see that now on the next slides, because we're gonna need that for the calculation of the setup and hold time requirements. And in the end, to retrieve the frequency, we can toggle the register stages here. All right, so we're still with task C, and next step would be to calculate the maximum frequency we can use. There's also a hint given already, which is the setup requirement. It consists of T, TQ, TPD, and TSTP, which is smaller than T period. So this is the setup frequency. There have been already some questions about what those stand for, those variables. So TC to Q is like the time a register needs to get an output on the signal Q after a clock edge arrived. Then we have TPD. TPD is the propagation delay, so the delay of the combinatorial logic in between the two register stages. And then there's also T setup. So this is our setup time we need for the registers. And overall, they should be smaller than T period. And T period is like the period of the frequency we want to, or we can run the circuit with. All right, so maybe we first have a short introduction again to the setup and hold time requirements. So maybe let's imagine we have a flip-flop, and at a certain time we want to, so this is our clock, and this is our data that comes into our flip-flop. And at some point, we change the data. And then the interesting question is, at what point in time does it arrive at the output? So there are multiple cases, right? So it could be the case that if D changes before the clock arrives, and that with a certain time, then we already see it here at the output, right? But if it's like slightly behind the rising clock edge here, then it will show up at the output with the second rising clock edge. So why does this matter now? So what happens if we have a look at the time span around a rising edge? So a little bit before the rising edge, a little bit after the rising edge. It could be the case if now D changes exactly in that time window, yeah, maybe it either already latches through and we get this behavior or not, then we would get this behavior. And that this does not happen, we define like a certain area around the clock edge, which is either the setup or the hold window, either if it's on the one or the other side of it. And this is like how we come to more or less those equations here. So the setup time requirement and also a hold time requirement. Questions regarding that? No. Okay. Then I would say next thing for you is like calculate the frequency for the given circuit. You should also see underneath the diagram like numbers for our registers. So what is the expected time TQ of our register? What setup time does it have? And what is the hold time of the register? All right. So I would shortly give another explanation to the setup time. So this is our register, right? So you have here somehow like a data. And on the other side, we have our Q, right? And somewhere we have our clock that also needs to get into the register. And the interesting part is now what we want to figure out is the time span which we have from here to here, right? So this is our T, let's call it T clock. So this is the time window which we have, which a signal can travel from here to here until the next rising clock, right? So it needs to be stable until it arrives here so that it is stored correctly. And now we have like three things we need to think about. So this is the time span, which is if we get a rising clock edge here, we have a time span that is needed until like we actually have a Q at the output. So this is like our T clock to Q. Then we have the time span that is needed for the signal to traverse through our combinatorial logic. This is then like T PD. And then we have another time window where our signal needs to be stable until the next rising clock edge arrives. And this is then T setup of the second register. So this is like the second register expect that during that time window the signal does not change, because this is like compensating for the fact that if it would change and we have like some small variance in the clock, then we would sample just the wrong value. So it needs to be stable for a certain amount of time, and that is dependent on how the register physically behaves. So I guess I just continue. All right. So let's see. So as I already mentioned, we need a setup time in order to get to T period, which in the end will give us our frequency. So we just use this formula, add in all the values, come to 2.14 nanoseconds. Our T period needs to be larger than that. And so what is our frequency? Our maximum frequency, it's just like 1 divided by T period, and this gives us 467 megahertz. Questions? No? All right. Then I would say we just do that once more. This already gives the answer, right? So now we come to the question D and want to see what can you do to increase the maximum frequencies, and we want to have two drawbacks of the approach we can use for that. All right, I would come to the solution to that question. So an easy option would be to just split the longest path between the register stages, because this is like the only option we have, right? Because we cannot change the registers as a logic designer. That's like a element we just can use as it is. So the T, C to Q, and also the T setup is like a fixed value we need to live with. So the only option we have is like to change the propagation delay. And one way to do that is that we add just another register stage. So this is a very usual approach. If you design a lot of digital systems, then you think about, okay, is the frequency high enough that I want to use? And if not, then you're probably gonna add register stages to your combinatorial path. But there are some drawbacks to this approach. It is true that now the longest critical path resides here, because this is the gate that has the longest delay. So it doesn't matter what those here have if this one is the largest one, right? So even over the register stages, so if there would be multiple, you just pick the one with the longest propagation delay. Nevertheless, in between which register stage, because the frequency you would clock all registers is the exact same. So you need to pick the worst case scenario, which in this case is. So now our maximum frequency is 649 megahertz. But what's the issue here? First thing is we added another register stage. This costs us another register stage, meaning that the area increases. And the other thing is like that now we need 2 clock cycles until the result is at this register state, right? Because during the first clock cycle, the data transverses to here, and then during the second to here. And this is like the result we want, so we need 2 cycles instead of 1. Questions? No. All right. Then I would say we do everything again. We state the Boolean functions for g, h, and I, calculate the propagation delay for all paths, identify the critical path, and then we calculate the frequency for this circuit now. So I give you like around 5 minutes, maybe a little bit more for this. If you have any questions, raise your hand and I will come and help you out, ask. All right, I'm gonna show you the answer to this question. So first question, what are the Boolean functions? So G, so we go back all the way backwards, right? So we look what is the path, what are the paths going to G, which are those 2. And then we see, okay, the first gate is like A and B, and then the second gate is the result of A and B, and again with E, so we get G is A, B, E. Same thing for H again, so we have like C and D, and there's our NOT gate, so it's not CD. And we have I, so same thing here, going backwards, seeing, okay, this gate and this gate. Then we have C and D, and the result is ended again with F, so we get I as CDF. So now the question, what are the propagation delays for the functions? So for TG, the longest path is like through those 2, which is why we have 2 times the delay of an AND gate, which is 1.2. For TH, we have exactly this path through those 2 gates, which is then TAND plus T0, makes 0.8 nanosecond. Yes? You should definitely not, because like this is like in the end what you want to get, right? So you want to have like the T clock. So you want to get like the delay from here to here. And this is like more or less T clock. This is what I tried to explain before with what I painted on the board. But so maybe what makes you say that T clock should be part of it? Makes the setup time, or you mean this one, right?
Yes, that's good.
Yeah, so this is clock to Q. This is, okay, the difference here is like that this is actually referring to this one here, to clock to Q. It's just like that on the lecture slide, clock is written out completely, or it's like CLK, and here it's just C, but this refers to this number here. So, okay, so the idea is like what you want to get in the end is like the time you have from here to here, right? This is like the time T clock. So this is like the inverse of the frequency you want to clock your clock with. And now, in order to calculate T clock, you need to add up the time that is needed from an arriving clock edge until you get Q. This is then T CQ. Then you add to this one the propagation delay of your combinatorial circuit. This is TPD for propagation delay. And then on the second register stage, you need to make sure that the signal is stable for a certain amount in time, right? And this is referred to the T setup time that needs to be added here before the next rising clock edge arrives, right? So this is then one rising clock edge here and the other one here. And this is then F clock, 1 divided by T clock. And usually you have like here a clock input, and this is then our clock you clock the registers with. Is that clear now, or please ask again if it's, yeah? Okay. All right, so continuing with the I function is like then 2 times the T AND gate, because the path goes through both of them, which makes 1.2 nanoseconds. Now, what is the critical path? Yeah, we have 2 options because both of them are identical long. So either we choose Ti or we choose Tg. And now the question is, what is the maximum frequency? So same as before. We need the setup time requirement for this one, and just adding the numbers. So TCQ is given, TPD is the critical path we recently calculated, and T setup is also given. We get our 1.54 nanoseconds, and just dividing 1 by those 1.45 nanoseconds gives us roughly 650 megahertz. All right, so maybe one short remark regarding the hold time requirement, because we haven't used it for the calculation of the frequency, right? And you don't need that therefore. But you still have like this issue that at this register here, it is important that also after the clock edge arrived here, the signal still is stable, because otherwise we could have this issue I explained earlier, that the maybe already get latched through if it would change at this point in time. So you need to make sure that this does not happen. So the thing is, if T hold is larger than the smallest gate here, so for example, if we wouldn't have this gate here and would just connect this, then we would have a hold time violation, right? Because then the signal would be faster from here to here than our hold time would be. So just as a remark. And in order to avoid such situations, you just add gates in between. So the simplest option would be, in order to not change its behavior then, just adding 2 NOTs. So 2 inverters, and that's it. So if we would assume that this path here would be violating the hold time, then solving this thing is just like adding 2 inverters here. questions regarding setup and hold time? No. All right. Then let's continue with the next task. And we want to calculate the mean time between failures. So imagine that we have a device running at 100 megahertz, and there is a sensor connected to it that sends data over a UART connection with a baud rate of 115,200. Question A asks us to calculate the mean time between failures. It already gives us some numbers, especially the technology dependent value and also T0, so the time window for a metastability event to be able to be happening. And yeah, I guess we start with question A. So don't be afraid, especially for the examination in the end. We wouldn't expect that you know this formula by heart. Okay, so just look it up for now, and during the exam we would just provide you with the formula. All right, so this should be the formula you hopefully found in your lecture slide. Maybe a short introduction how this formula works. So first thing we need to think about is, like, if we think again about this formula, it was about, okay, we have like two different clock domains, right? So what happens if one register is clocked with the one clock and the other register with another clock? And if that's the case, then we don't have the assurance anymore that all the requirements for the flip-flops are met. So it could be the case that we change the data in signal at a point in time where it shouldn't be changed, which leads to metastability, or could lead to metastability. And now, if we think about FD, so FD is like the frequency which our UART is running on. So this is some kind of frequency, and usually that is more or less very, very slow. So this time window here is like T of FD, and now we have a look at the time window at which a metastable event could happen. And this is like, yeah, when does the data change in this clock domain? It always changes on rising edges, right? So we have a change at that point in time. We might have a change at that point in time, like in that point. Then we have a change that, and so on. So it could be either a 1 or a 0, then there might be a change and there might be a change. And now the question is, when can a metastable event then happen? And this can only happen in a time window that is that small, right? So this is then referred to as our T0. Only if we sample at this time window this signal with FC, which is our sampling clock then, and if a rising edge of this happens to be exactly at this time window, then we have the case where a metastable event can happen. In all other cases, it won't. So if this frequency of our sampling happens like this, it might be the case that we also have a sampling at that point in time, right? But this point in time does not happen during the small time window. So no metastability event can occur. So if we now look at probabilities, then the probability that we fall inside this time window is just like T over TFD. which is nothing less than T0 times Fd, all right? So this is the probability that such a metastability event can even happen. And then we have like the second part here, which is our exponent Tr divided by tau r. So this part here can be also written as this, right? It's just the opposite. So it's just dividing it. And then this describes the probability that the metastable event does not settle in the tau r. And this is like the problematic case that this metastable event occurs and is persistent. This is the probability that is described through this functionality. So now we have then T0 times Fd, the probability that a metastable event can happen, times the probability that it does not settle in time. And this describes like now the probability that we get an error per second if we multiply this now with the frequency we sample, which is Fc. Yes? Fc is that one. So this is the sampling frequency. So this is the clock of the second flip-flop, right? So we have then like one flip-flop that runs with a clock from the clock domain Fd. And then we have a sampling clock that runs in the Fc clock domain. Yeah. Okay, you don't need to remember like the exact form of this function. I hope this helped a little bit to understand why it looks like that, and hopefully also helped to understand the meaning of the different parts of the functions. If not, please feel to ask. It should also help with answering question number B. But first, let's stick to placing some numbers in there. So we already got those numbers. We got tau Tr, tau r. Just place them in there. Also, we already have T0. Place it in here. And now the question is like, what is Fc and what is Fd? And so the baud rate of UART corresponds to the frequency with which the UART is running on. And this is, yes? Yeah, the baud rate is the frequency. Yeah. And it is the frequency we want to sample. And this is then like this one here, right? So this is our baud rate. And Fc is the sampling clock, which the device is running on. And these are the 100 megahertz. So maybe a little bit of explanation for this UART. Maybe I do it here. It's like, so UART consists of two signals, Rx and Tx. And Rx is like the receiving signal, which comes then in. And this happens with a certain baud rate. And this corresponds to the frequency. So here we get then our baud rate. And since UART is an asynchronous interface, we need to think of, okay, this is like how the data could change, but let's assume it also changes like every clock cycle. And now we want to know, is this currently a 1 or a 0? So you need to sample that. And what the system that is receiving the data over UART needs to do is then, it needs to sample the data with a certain frequency, right? And see whether it is 1 or it is 0. And this should also happen with a certain frequency, which is now referred to FC. Yeah? Atom seconds. Atom seconds. Very small. 10 point, not entirely sure. I guess it's like 15? I don't know. Look that up. Yeah. Yeah, I think the issue is that this is like 9.4 atom seconds. Yeah. Yeah. It's really small. So what is TR standing for? As said before, this expression here describes like the probability that a metastable event does not settle in a certain amount of time, and this certain amount of time is TR. So you could also say this is the time a potential metastable signal has to resolve in order to be correctly handled. And now the question is, what happens if we increase TR? This means we give the metastable signal more time to settle, and this results in that the probability decreases, right? That we get a not settling metastable event. And this also means then that the mean time between failure increases if we increase TR. So we can also double check that by just doubling TR. If we double TR, do the calculations again, we see that we now expect a failure in 142,000 years. Questions so far? No. All right, then I will give you some time to answer C. Or has everyone already answered C? Okay, then I will just give you some minutes. All right, so how do we calculate the result of this question? So what is the time span? As I said before, we need to calculate it once for the worst case and once for the best case scenario. So we pick it either like 3 hours or 5 hours. And yeah, what do? You take the mean time between failure. And since you have 1,000 devices, this mean time between failure distributes over those 1,000 devices. So you just divide it by 1,000. And the second part of the question tells you that the devices only operates like 3 or 5 hours, or between 3 and 5 hours a day. So for the first calculation, we just choose 3 hours. So the effective working time of those 1,000 devices is just like 3 divided by 24. And so you just divide the mean time between failures also by that number. And then you come to 0.8 years. And you do the same thing for 5 hours a day. Then you get to 0.48 years and result with a time span of 0.48 to 0.8 years in which we expect a failure of those 1,000 devices. Questions? No. All right. Then let's continue with the next topic for the day, which is logic implementation. And this is like the task for the logic implementation. So we consider the following circuit elements. We have a D flip-flop with asynchronous clear, which is like the FDCE, and we have a D flip-flop with synchronous set and clear, which is the FDRSE. There are also some pictures of those two, and the third one is the lookup table of size 4, so meaning that it has 4 inputs and it can implement any 4 input functions. So how do they look like? So these are the components we are allowed to use. So we have our 4-input lookup table. We can realize exactly one function. So the output is dependent on those 4 inputs. We have our FDCE. It is a flip-flop that comes with a clock enable, a clear, and a clocking signal. And then we have the second type, which is the FDRSE, which additionally comes with a set signal. So you cannot only clear it, you can also set it. Now the question is we want to implement a certain logic functionality, and this is like our logic function, y should be equal to a or b and c and d and e, and we want to store the result in a flip-flop. Question is, how can we, so the first question is what is the purpose of each input and output signal, and the rest of the available logic blocks. So I will just come to the solution for this one because I guess it's kind of obvious. So we talked about lookup tables already. We have our 4 input signals, we have the 1 output signals. For the flip-flops, D stands for data input. We have our clock enable, which abbreviation is CE. We have our clock. We have our clear, which means that if clear is set, the output is set to 0. We have our normal Q, so our data output of the flip-flop, and the additional set, at least for one type of the flip-flops, and this sets the output to a logic 1. So now the interesting task is we want to implement now this logic functionality using those modules, and we have a bit of a restriction. We want to use the lookup table and one of the flip-flops or the other one. Now the question is how many lookup tables, how many flip-flops do we need to realize the functionality and store its value in a register or in a flip-flop. All right, then let's have a look at how to do that for the first case. So one lookup table or multiple ones, and we want to use a flip-flop without the set functionality. So maybe first thing you need to think about is how many variables do we have in our function. So if we go one slide back, we see, okay, we have A, B, C, D, E. So we have 5 inputs, but we only have a lookup table that can support 4. So we need at least 2 lookup tables for doing so. So this is how it looks then. The easiest option is like, okay, for the end, we only have 4 variables, so we can easily end those together using one lookup table. And then we need another lookup table for the ORing of the A input, and then we get our logic functionality we want to feed to our register or our flip-flop and feed it in, and that's it. Question regarding that? Yes? For this one you mean? Yes. You don't care actually. So you would assume that it is a don't care and configure the lookup table also that way, right? So then the output is independent of whether all the other 3 inputs are either 1 or 0. Yeah. Other questions? So has anyone an idea what changes now if we have a flip-flop that also supports a set of its output? Yeah, very good. So that's the solution. So we then only need one lookup table anymore, so we can save on resources. We are doing the end again on the lookup table and use A as the set for the flip-flop. Questions? All right. Then maybe a short break, 3 minutes, something like that. And then we dig into the next topic, which are FIFO, so first in, first out buffers. But first, like 3 minutes of short break. So, all right, maybe before we dig into the topic of FIFOs for the rest of today's tutorial, a short recap of lookup tables, gates, and what are the difference, what do they do. So imagine a logic function, so a functionality you want to realize. So this could be something very simple. So for example, you have your logic function and your logic function is, I don't know, f is a and b or c. You want to realize this. So now you have two options, or maybe three options. So either you use a CPU, write software that realizes that, or you use hardware. Either you use an FPGA or you use an ASIC, so an application-specific integrated circuit. They both differ a little bit, right, in the elements you can use to realize this functionality. For an ASIC, you use usually gates to realize this functionality. So there you have then an AND, OR, NOR, whatever gate your chip vendor allows you to use. Or you use the FPGA. And on an FPGA, you don't have those gates. But what you have instead are lookup tables. So there you use lookup tables to realize this functionality. So any questions regarding this statement? Does this clarify things, hopefully? All right. Okay, then for the rest of today's tutorial, we're gonna have a look at FIFO and what are they used for, and maybe also how you could implement them. So FIFOs are usually in between different modules that transfer data with each other. So a very common example is like we have module A transferring data to module B, and maybe module A is sending data faster than module B retrieves it, so or can process the data, so we need some kind of buffer in between. And what you usually use is a FIFO. So module A places then the data in FIFO, and module B reads the data out of the FIFO. And a asynchronous FIFO has the benefit that you now can clock the input and the output at different frequencies. So we have now module A transferring data to module B, and module A is doing so with a frequency of 500 megahertz, and module B is just running on 50 megahertz and reads the data out from the FIFO. So now we are gonna answer the following questions, which is very important to understand for now, is that the burst size of module A sending data is 500. So meaning that module A sends 500 packets of data, then makes a break for some amount of time, and we currently don't care about this amount of time, and then it sends the next packets, again 500 in a row, makes a break again, and so on. And now the question is, what should be the depth of the FIFO, so that we can ensure that no loss of data happens? Any ideas how to start with these questions, or just question marks? How many nanoseconds take for what? It's a very good question. Yeah, so this is exactly the right question we need to answer, right? So how many nanoseconds do we send data, and how many nanoseconds do we receive data? We know that module A works at 500 megahertz and sends 500 packets, okay? So now you can calculate how much time does module A need to send 500 packets. So you know the frequency, right? Yes. So you can calculate how much time is needed to send 500 packets. So one packet is sent every clock cycle. And then you get a time span for how long it needs to send 500 packets. And then you can go the other way around, see, okay, module B, how many packets can it receive in that amount of time? And then you know, okay, this is the amount of packets that are read in the time module A has sent the packets, and the rest of the packets need to be buffered somewhere else, which is our FIFO. All right, then let's talk about the solution to that answer. So first step is like noticing, okay, module A runs at 500 megahertz. So this means this is a 2 nanosecond clock period. So every 2 nanoseconds, a data packet is sent. So now we know from the question that the burst size is 500. So multiplying 500 by 2 nanoseconds gives us the transmission time of those 500 packets, which are 1000 nanoseconds. Now we think the same thing for module B, but think it more like out of a perspective, how many packets can it receive in the same time? So we know B runs at 50 megahertz. So the clock period is 20 nanoseconds, meaning that module B can receive every 20 nanoseconds a packet from module A. So, and now we know A stands for 1000 nanoseconds. So we will divide this by 20 nanoseconds, which receiving of one packet takes us, and we end up with 50 packets module B can receive during the time module A sends out the burst of 500 packets. And this brings us to the solution of the FIFO size. So while A sends 500 packets, B can only read 50. So the buffer in between needs to be as large as the difference of those. So it needs to be 450 packets large. Questions? Yes, that is the number of packets the FIFO needs to store. So if you build a FIFO, you usually think of, okay, you have a certain packet size, so this is your packet, and you usually refer to this as your FIFO width. So this is your width. And then the question is, how deep is this? So what's the depth? And this is like the number of packets. Make sense? Any other questions? Okay. Then I would directly come to answering question B. What happens if module A does not send packets in a burst-sized manner? So sending 500 packets, making a break, and then waiting for a time, and directly sending another 500. If it doesn't do that and continuously just sends data, yeah, how large should be our FIFO? It should be indefinitely large, right? Infinite large, because it's just like not possible to receive enough data for module B if there's not a break in between, right? So this is a kind of not solvable application scenario. So if you now think about designing a system and think, okay, would it make sense to let one part of your system run at a higher frequency than another part, then it definitely makes also sense to think about, does it even